Okay, I believe we are live. Let me just check the audio and make sure things are working. I should be able to do that in a second. Okay. Yeah. Alright guys, welcome back. So this is the first video in this series, so therefore I'm going to talk a little bit about what's going on. So I stopped making the Golang tutorials at, I think, part 10, because I just started college. I don't really have a lot of time to do that. If you want to check those out, there's a playlist in my channel. Go check those out. They're very interesting. But since I started college, I've been doing this physics course, which has been pretty difficult, and I need to find a nice way to review it, and I figured the best way to review it would be to actually teach it. So I have this setup here, and I'll be going over my lectures, going over the notes, and basically just teaching it and saving it on YouTube, which could be fun because you could learn with me, I could look back at it as a reference in future, and so that will be fun. Okay, I plan to make one video per every lecture that I have, so I've already had 2. That means that I have 2 to do. I'm using this nice setup over here. I'm sorry if the writing is not good in this video. I already ordered a stylus, which will come at some point, and then the writing will get better. And in this video, we're going to start with the first lecture, which is all about vectors. So just to be clear, this will be a calculus-based physics situation, which will be interesting for me since I've never taken a calculus class, but I know enough to get through physics, I think. And anyway, this video will not have any calculus in it, I don't think. Okay, so anything else that needs to be talked about? I don't think I need to discuss anything else, so let us just get right into it. Okay, like I said, this video will be about vectors. So the first question is, what are they? And the they is vector. How do you spell vectors? Vectors. So what is a vector? Well, here's a basic overview. So first of all, they're very useful when it comes to describing situations in mechanics, which is the physics thing that these videos will be focusing on. Mechanics is an area in physics as opposed to electricity and magnetism. It's all about forces and Newton, basically. So vectors are very useful for describing equations and formulas in mechanics in a compact manner. They make it very clear to write. So the basic definition of a vector is that it's a directed, and I'm going to underline that, it's a directed line segment, I don't know, sure, why not, segment. It's a directed line segment. What does this mean? Well, it's basically just a line, but with a direction. So here we have a line. That's a line. And to give it a direction, we would go like this. So there you go. Now this is a directed line segment. It's an arrow. So vectors are commonly denoted by arrows, and you could also give them names. So we could give this vector name. We could call it A. This is vector A, and every vector will have a line on top of it to denote that it's a vector. Sometimes you'll see actually vectors denoted as A with an arrow over it. That's a little bit more complicated to draw, and that's why I'm not going to be using that notation, but it's basically the same thing. So A with a line over it is a vector. So let's give this guy his line again. Okay, so what are their properties? What do vectors have? They're like an abstract mathematical idea, but what really do they have? So let's make a new page, and let's talk a little bit about what exactly vectors have. So they have a magnitude. Oh boy, that's not how I spell magnitude. Magnitude. This is like a number. So, okay, well, all of these will be numbers. Magnitude will be like size. That's also we could call this size. Or length. Size. Basically how big it is. They also have an orientation. Orientation. I don't know how to spell orientation. I really don't know how to spell. I apologize. Orientation. And the orientation will be an angle, some angle. Usually with respect to the origin. Not to the origin, I'm sorry. Usually with respect to the horizontal. So for example, if we make... Can I make dotted lines with this software? I wonder. I don't actually know. It's possible. If I have... I don't actually know if I can make dotted lines. So okay, so I'm just gonna make a dotted line to denote the horizontal. So imagine this is the horizontal, and we have a vector over here, this would have some kind of angle. And sorry, let's draw that a little bit nicer. So it'll have some kind of angle, and we could call that theta. So it has a magnitude, it has an orientation, which is an angle, and then it will also have dimensions, which we'll talk about in a second. So I'm going to get into that. But first of all, so imagine we have this vector over here. We could call this vector A with a line over it. So the magnitude, or the size, this would be, yeah, this would be like like it has an absolute value of A. So what is the length of A, essentially, is what this is asking. Like, I don't care about what direction A is in. What is the length of A? And this could also be denoted as simply just normal A. A without the line over it would just be the magnitude. How long is the vector? And then you also have the orientation, which is an angle, as we see over here, theta, which basically theta will tell you the direction. If theta is 90 degrees, the direction will be up, like yeah. So here we have a vector with 90 degrees of orientation with respect to the horizontal. If the orientation is 180 degrees, it will be like to the left. So we could have here. Let's draw that clearly. Hold on. Yeah, we could have a vector with an angle like this, and that would be 180 degrees, or it could be pi. Pi is another way to denote angles in radians. Normally I will use pi because they're easier. So like pi over 2 would be 90 degrees, and that's the angle. So the angle tells you the direction of the vector, and then you can figure out, and the magnitude tells you how big it is. So those are the two main things. The other thing that a vector will have, and this is another way that you could write vectors. So imagine for example, I have here, this is like the horizontal, and I have a vector just pointing up. And we could call this A hat. Not A hat, sorry, A with a line over it. So this is a vector. And imagine I tell you that that A, the magnitude of A, equals, let's say, 8. It's 8 units long. Units are a different thing that we'll talk about. Like, it can either be meters, feet, etc. So it's 8 units long. And then theta equals 90 degrees. You know what, I'll do pi over 2. Pi over 2. So that's its angle. It's pointing directly up. So then we can also talk about vector A in terms of its dimensions. We didn't cover this in the lecture at this point, but I think it's important to note that you could actually write vector A equals, and normally you would want to show this as a tuple, so parentheses. It would be 0 in the x direction, so it's not going anywhere in terms of horizontally, but it's going 8 in the y direction. And so you see it has these components in the x and the y. And if you're in 3 dimensions, it'll have 3 components. But you could write vectors in their dimension format as opposed to their length and orientation format. And that will become useful. This format of dimensions will become useful for doing certain operations, algebraically, that is. Okay, so that is a brief overview of, very simply, what vectors are. Let's go back to page 1. We can pretty much erase all of this, I believe. I just don't want to make too many pages is the thing. So, okay, let's talk a little bit about some of the things that we could do with vectors. Or rather, wait, I want to cover one more topic just in basic overview of vectors. Let's talk about what a unit vector is. So, unit vectors. So if you've ever taken trigonometry, you've heard about the idea of a unit circle. The unit circle is basically like the simplest idea of circle. It's a circle with a radius of 1, correct? Great. So that is a unit circle. So a unit vector is very similar. It's basically like, what is the simplest vector? And that means a vector with a magnitude of 1. So you know what, from now on, whenever I write vector, I'm just going to write vec, short for vector. So vec with mag equal to 1. It's any vector with a magnitude equal to 1 are the unit vectors. And they're usually denoted as A with a hat. So A hat would be a unit vector. From this it follows, and it will follow shortly once we talk about some of the operations you could do with vectors, that A hat equals the vector A, the normal standard vector A, divided by the absolute value, the magnitude of vector A. So it's basically, if vector A had a magnitude of 5, then vector A divided by 5, the magnitude would become 1, and the orientation would be the same. So that way you can imagine that vector A looks something like this. This could be vector A. Then therefore, A hat would look something like this. I don't know. Its orientation is the exact same, but the length has become 1 unit. That's why it's called a unit vector. It's a vector with 1 unit. Okay, hopefully that makes everything clear. By the way, if there are any questions, leave it in the comments. I'll happily go over them and answer them. Okay, so now let's talk about what are some of the operations that we could do with vectors. So we could do some algebra with vectors. If you want to say that vector A equals vector B, what are you claiming when you say that vector A equals B? Well, when you say this, you're claiming that they are the same vector. So that means that the magnitude of vector A equals the magnitude of vector B, and I'm going to do a colon over here, and their angles are the same. So you're claiming that they have their same length, they are the same length, and their angles are the same. Now, this definition is important to really understand, so I'm gonna make something very clear. Imagine we have our x and y axis, so we're going to be working in 2 dimensions. So here's an x and y axis, and we're only working with the positive values for now. I could have a vector over here, and I could call this vector A. I could have another vector over here, and I could call this vector B. Now I tried to draw them similar, and take my word for it, even though they don't look it, these are the same. Like the angle is the same and their magnitude is the same. But even though they're not in the same place, I could still say that vector A equals vector B. They are the same vector. So that shows you that the only thing that's important for a vector is its magnitude, its size, and its orientation, the angle. Where it is in space doesn't matter at all. It's just about those 2 things, its magnitude and its orientation. And so this statement, vector A equals vector B, is true. Great. So that is what you do when you claim that vector A equals vector B. Additionally, what you claim, sorry, that was a mistake. Additionally, what you claim is, I'm going to go to another page for a second, just because I don't want to erase everything in that page yet. Additionally, what you claim when you say that vector A equals B, do you remember the dimension format that I said about vectors, that we could say vector A equals a tuple, so of A sub x, comma, B sub x, sorry, A sub x, comma, A sub y. That's another way you could write vectors. So we could also say B, the vector B, equals B sub x, which is not a vector. B sub x is not a vector, by the way. It's simply a number. It's the amount of units that vector B travels in the x direction. And it could be negative, too. B sub x, comma, not A, but B sub y. I'm gonna erase that. B sub y. Okay. When you claim that A, vector A, equals vector B, it follows, and this should be fairly intuitive, that A sub x equals B sub x, and these are numbers again, so we understand what saying a number equals a number means, and if you don't, then you're a philosophy person and you should learn philosophy. And then it also follows that A sub y equals B sub y. So it's basically saying the amount of distance that A travels in the x direction equals the amount of distance that B travels in the x direction, and also the amount of distance that A travels in the y direction equals the amount of distance that B travels in the y direction. So that is the same definition basically as what we had written over here, that all that matters is how far they go and in what direction they're traveling. If these numbers have the same sign, like if A sub x is positive, then B sub x needs to be positive as well, so that their direction, the direction the arrows are pointing, is the same. So both of these definitions of vector A equals vector B are compatible. They mean the same thing. This is just a different way of writing it. Okay, now let's talk about some of the operations that we could do. So the first one I want to talk about is scalar multiplication. So we've spent the entire video so far talking about vectors. Let's review what a scalar is. A scalar is just a number. So a sub x is a scalar. 5 is a scalar. These are things that are just straight up numbers. They're values of magnitude essentially. So scalar multiplication of a vector would look something like this. It would look like vector a times b, which is a scalar, or alternatively b times vector a. That is scalar multiplication. So what is happening when you do this? Well, you will get a vector back. So yeah, this is a little bit confusing. So I'm gonna erase this. It's a little bit confusing. Sorry, that was a mistake. Yeah, scalar multiplication would look like b times vector a is going to give you back another vector, and we'll call this c, vector c. What will vector c be? Well, vector c will have a magnitude, so the magnitude of vector c will equal the magnitude of vector a times the absolute value of b. So actually, hold on. Times the absolute value of b. Why am I saying the absolute value of b? Well, if b is -5, then that won't affect the magnitude. Like, magnitude is always positive. You don't have a negative magnitude when it comes to vectors. What you do have is angles. So let's demonstrate this. Let's talk about this for a second, because this is important. Suppose we have, and I know I just erased it, but suppose we have our x and y axis, like this. And I have vector a over here. I don't know why I drew the arrow part of that vector so big. We have vector a over here. Great. The magnitude of vector a is a positive number. I'm just asking for the length. How big is vector a? So this is going to be the absolute value of vector a. Imagine I have another vector. No, I'm good. Imagine I have another vector, and I'll call this vector b. Vector b also has a magnitude, and its magnitude is also positive. The magnitude is always positive. So vector b has maybe the same magnitude as vector a. I wanted them to have the same magnitude, but I drew vector b too short. But anyway, vector b has the same magnitude of vector a, even though they're facing opposite directions. What is the difference with these vectors? Because they're clearly not the same. The difference is the angle with respect to the horizontal. Vector b has an angle that's clearly greater than pi. It looks a little bit like pi. It looks a little bit like, I don't know, 3/4 pi or something like that. No, that doesn't make sense. Anyway, vector b has an angle that's greater than pi. Vector a has an angle that's less than pi over 2 even. So they're facing opposite directions, and the angle is what allows them to face opposite directions. So bringing this back up to here, our scalar multiplication, the magnitude of vector c will equal the magnitude of vector a times the absolute value of vector b. So if vector a had a magnitude of, let's say, 3, and b is 5, then vector c will have a magnitude, the thing we get back will have a magnitude of 15. If vector a had a magnitude of 3 and b was -5, vector c would also have a magnitude of 15, but the angle, we will add 180 degrees to the angle. It's the sign of vector b can flip the vector. Sorry, the sign of b is not a vector, the sign of b can flip the vector depending on what the sign is. If the sign is positive, then it will be the same, and if the sign is negative, then it will be flipped around. So let's make this very concrete. Let's just show this very clearly. So let's erase what we have on this x and y axis, and let's make this very clear. I hope I can draw this in a reasonable manner. In fact, you know what? I think I will try to really design this x and y axis to be very nice so that we could use it in a nice way. So let's draw one line for the y axis, one line for the x axis, and now let's show. Here's our vector a. This is vector a. Now this can be 2 times vector A. Okay? So it's the same angle as vector A, it's just twice as long. And then we have this. That was a mistake. This is negative 2 times vector A. So you see it was flipped around. Now that's the only thing that the scalar could do. It's not able to like slightly tweak the angle. It's either able to flip it around or keep it the same. But notice how the magnitude of negative 2 times vector A equals the magnitude of 2 times vector A. They're the same length, they just have different angles. It would not be correct to say that negative 2 times vector A equals 2 times vector A. They're different vectors because they're facing different directions. Okay, great. I think that covers scalar multiplication. Let's move on to the next operation that we could do, which would, oh, actually, there's one thing that I had written here. What is this? This is a cool formula. Okay, I'm not sure how important this is, but let's talk about this for a second. So, yeah, let's erase this stuff, and let us dissect what I have written over here. So, imagine we have B times vector A equals vector C. Right? We're getting familiar with this idea. From this it follows that, recall that C hat, the unit vector related to C, equals vector C over the absolute value of vector C. In other words, the magnitude of vector C. Okay, so from this it follows that B times vector A over, which is vector C, over the absolute value of B times the absolute value of vector A. Yeah, that B times the absolute value of vector A over the absolute value of B times the absolute value of vector A equals C hat. Which further we could say, I have to erase this. Further we could say that this follows that we can simply say that right, so we can divide these into their components. We could say that B over the absolute value of B, B times the absolute, times A hat equals C hat. So here we have the correlation between the unit vectors, and we're just basically getting rid of the scalar. Like the scalar, we're decreasing its magnitude completely. Now, one thing that is interesting to me that I'm not 100% sure is, why do we have the absolute value of vector B times the absolute value of vector A? Why can't we just have the absolute value of vector B times vector A as an absolute value in itself? Like why is this part not, or rather, really what I'm questioning is, why is this part not just be vector A absolute valued, which would be the absolute value of vector C? I think, yeah, this would be like this would be the magnitude of vector C, I believe. So the reason why, it may be that I read it wrong in my notes, honestly, because this does make sense. Like this equals the absolute value of vector C fully, because what's inside of here equals vector C. Yeah, so the best thing I'm going to have to say is that I wrote this wrong in my notes. I don't think this is correct. And yeah, I don't see why we would need we would need the absolute value here either. In fact, I think that having the absolute value there could be a problem. Like, what if B is negative? Does this follow? Is this true? Unclear. Hold on, please. Is there a way to go between pages such that I don't have to? Okay. So, okay, stop it. Okay, this seems to be just a problem that I have in my notes, I think. Hold on, I just edited something so that I could see the entire page here, but I want to make sure that that's not a problem with the screen recording software that I have. Yeah, hold on. Give me a second to just edit something. Let's let's get this guy over here and this guy over here. And then yeah, we could have that like that, I suppose. Yeah, okay, this looks fine. That way I don't have to scroll down the page every time. Okay, so I mean I still will have to scroll down the page every time. No, okay, I'm not sure what I want. I'm not sure what I want in terms of zooming in and zooming out. But anyway, let's get back into the math. I think this should be fine, the setup we have. So this does confuse me. I'm not sure exactly why my notes have the absolute value. I just want to make sure. So let's do some concrete examples. Let's really dig into the meat and potatoes. Let's plug in numbers and let's see what we have. So imagine we have 5 times vector a. You know what? Let's do -5 times vector a just so that I know what would happen if it's negative, because that's the key thing. And let's say that vector a the absolute value of vector a equals, let's say, 10, and the theta of vector a, I don't know how to denote that, but the starting theta of vector a, let's just say it's 0 for now. 0 degrees. I want this in degrees. It'll be easier to work with, I think. Okay, so now we have equals vector c. So now we could say that vector c, the magnitude of vector c equals 50, correct? And that theta of vector c, or actually no, I don't want this to be theta. I want this to be like a new symbol. So phi of vector c equals 180. We've like flipped it, right? 180 degrees. Great. Now let's see what I have in my notes. So what I have in my notes is that let's make this just finer maybe. What I have in my notes is that -5 times, no, I want that to be thicker. -5. I don't know why I kept deleting that. -5 times vector a over the absolute value of -5 times the magnitude of vector a equals c hat. So let's just make sure what c hat means. So the absolute value, so the magnitude of c hat equals 1, and in this case the angle would still be the same. It would be 180 degrees. Okay, so now let's figure this out. So -5. So this over here is just a hat. So here we have a hat, which would be fine, and then over here we have -5 over 5, which would be -1. So yeah, we do need to keep the sign. So yeah, -1 times a hat would equal c hat. This equals c hat. Yeah, that's true. Okay, so we need the absolute value at the bottom because we need to keep the sign. If we just straight up said b over b, that would get rid of the sign. There would be no difference if b is positive and b is negative. We need the absolute value so that we keep that difference, because division would cancel the negative. That's why we need the absolute value. Okay, that makes sense. I hope that's clear, that you see that when we have the absolute value at the bottom, we get the right answer. If, for example, let's make a new page. If, for example, we said that it would be -5 times vector a divided by -5. Sorry, I messed this up. -5 times, oh god, I messed the whole thing up. -5 times vector a over -5 times the absolute value of vector a. Then we would have it that 1 times a hat would equal c hat. And that's just not true. Like, c hat is the opposite of a hat in this case. Okay, but then I had the more general question, if you remember, why don't we just have the absolute value over the entire thing? Why don't we have the absolute value? So why don't we have it that b times vector a over the absolute value of b times vector a equals c hat? Why don't we have it like that? And the answer is, if we did have it like that, then we wouldn't be able to split them up. So remember, we want to have it that b over the absolute value of b equal times a hat. So we wouldn't be able to split them up. We wouldn't be able to like divide them down the middle over here if they were in the same absolute value. And I think that is the answer why we have to split them up, so that we could write that formula in a nice, clean way. Okay, very cool. So all that makes sense, I believe. Let's go back to what we were doing with the scalar multiplication. So yeah, so we just showed that, we just showed this. We just showed that, I don't know why I zoomed in there. We just showed that b over the absolute value of b times a hat equals c hat. Great, that is scalar multiplication. Now let's talk about something else. And for that, I'm actually going to go back to this slide. Sorry, hold on. For that, I'm going to go back to this page, because I want to use the x and y axis for a second. So let's erase, and let's do some work. So we're going to talk about scalar addition. Not scalar addition, sorry. Scalar addition is just addition. We're going to talk about vector addition. What does it mean to say that vector c equals vector a times plus vector b? What does this mean? Okay, well, let's talk about it in terms of the arrow notation, and then maybe later in the video we can talk about it in terms of the dimension notation, because the dimension notation is significantly easier to understand. It's just straight up addition. So here, let's come over here, and I need the x and y axis. So suppose we have that this is vector A, and that, let's say, this, I don't like that, that this is vector B. What does it mean to say, what is vector C? What does vector C look like? Well, you could do something very simple. What you do is you take vector B, we select vector B, and we bring it such that the tail of vector B is on the head of vector A. Sorry, why didn't that come? Sorry. We bring it such that the tail of vector B is on the head of vector A. And then you draw a line. You know what I always do this whenever I make these diagrams. Let's put vector A over here. Then what we do is we draw a line from vector A, from the tail of vector A to the head of vector B, and this is our new symbol, vector. This is our new vector, vector C. So I actually want to, I think that this is a good enough diagram for now. What I want to show, though, is that vector C also equals vector B plus vector A. That this makes sense, that you could switch them around and it's still okay. So let's redraw the whole thing. Let's say that. So what would that look like? So imagine we have vector A over here. I want to make them look very similar. So imagine we have vector A, and then we have vector B looked something like this, I believe. Something like that. So we could take vector A, now we would take vector, well, before we took vector, yeah, so now we would take vector A, and we would put it like that with vector B, so the tail to the head, again, and we would draw, let's make this in red, we would draw a brand new vector over here, and this would be our vector C. And you could see that these two vector C's are the same, except for the fact that they're a little bit different because I'm not perfect, but you see the general idea that you could switch them around and it still works. And this we could prove algebraically later. Okay, one thing that is important is the idea of subtraction. Once you have addition, you have subtraction instantly. So let's take a look what subtraction would look like. So imagine we have, so I want my x and y axis over here as well. please. So imagine I have the simple statement that vector C, you know, I'm gonna make this a little bit more professional. Let's say vector C equals vector A minus, and now let's choose another color. Let's say vector B. So we have vector C equals vector A minus vector B, and this should also be black, I feel like. So yeah, vector C equals vector A minus vector B. Okay, so let's draw this. So let's also establish that what this also means is that vector C equals vector A plus -1. Let's show that over here. This would be -1 times vector B, right? Because -1 times vector B, saying that vector A minus vector B, that's the same as saying vector A plus the opposite of vector B. So with that understanding, let's draw this down. So let's draw vector A. Imagine vector A looks something like this. And now let's draw vector B. Imagine vector B looks something like, I don't know, this. So to say vector A minus vector B, what we would do is we would take vector B, and we can draw the minus of vector B. We can draw like the opposite of vector B. So let's do that. And as you can see, no, stop it. Great. So this would be the, this is vector B, and this is negative vector B. And actually I'm gonna show the negative in yellow, just to keep pace with our negative. So this would be negative vector B. And what we would do for subtraction is we would take the negative vector B and we would still do the head and tail method, like this. Sorry, why is it selecting the entire thing? That's weird. I guess it's because it made the line the entire thing. So let's just draw that again, just by hand. So we would take the negative vector B and put that head and tail with vector A, negative vector B. And then we would draw vector C going from, again, vector A to vector B. And this would be vector C. Now, I want to note that this idea is the exact same thing as, imagine we have vector A over here again. We could take the positive of vector B. Yeah, we could take the positive of vector B and put it tail to tail with vector A, as opposed to head to tail. And then what you would do is you would draw from the, instead of drawing from the tail of vector A to the head of vector B, you would draw from the head of vector B to the head of vector A. And that will give you your vector C again. And you could see how this is the same idea. So that is addition and subtraction of vectors. Okay. Great. With that idea in our heads, let's move on to some more operations that we could do with vectors. Again, this is just a basic overview of what vectors are and how to use them. Oh no, I deleted my access. That's so sad. Okay, I'm going to need that back probably. Just a few more laws that you could test out pen and paper by yourself if you want. In fact, we could probably do that ourselves. We have a concept of, I should have covered this before when we were doing scalar multiplication, but I forgot clearly. We have a concept of that C times D times vector A. The laws of order of operations work just as they did before, so we could really do whatever we want. This equals C times D vector A, which equals CD vector A, which, is there any other combination that we could do? I guess we could say it equals, which equals D times C vector A, right? So let's actually, if you want, we can test that out. So let's come over here to where we have our numbers, and imagine we say that, let's say, we say that C equals 2, that b equals 3, that vector a is a vector where the magnitude of vector a equals, let's say, 4, 2, 3, 4, and the angle's not important because everything here is positive anyway. So actually, no, let's make it important. So c equals negative 2. C equals negative 2. And theta equals 0 degrees. Okay, so now let's try things out. So let's first try CB times vector A. So that would be negative 6 times vector A, which equals let's say vector C, such that the not vector C because we already have a C. Let's say vector D, such that and I'm going to draw this in a different color. This equals vector D, such that the magnitude of vector D equals 4 times negative 6 is 24, negative 24, so that equals negative 24. And let's say vector D's theta equals, well, now it's negative, so that would be 180 degrees. Great. Okay, now let's do the next way of doing things, which would be, let's say, negative 2 times 3 vector A. So this would be the same thing as, well, that would be the same thing as saying negative 2 times, let's say, we can call this vector E. And let's establish some things about vector E. So vector E, let's do this. Where should we write this? Let's just do it right over here. Vector E, its magnitude equals, well, 3 times 4 is 12, and its angle, theta, is still equal to 0 degrees because it hasn't been multiplied by a negative. And then let's actually go to let's go to a new page. We could say that what do we have? Negative 2 times vector E equals let's do red. Do we already have it? No, I don't think we have it red. So that equals vector F, such that the magnitude of vector F equals the magnitude of vector E, which was 12 times negative 2, so that equals negative 24. And the angle equals 180 degrees. So you see that it works, and you could try it out for the others, and that will work as well. The other thing I want to show is the idea of the distributive property. So that's another idea that we have from basic math. It basically states quite simply that, let's erase all of this. It states very simply that C times vector A plus vector B, that equals, that equals C plus C, and also C times vector A plus C times vector B. And let's get rid of that, and instead let's draw that properly. Stop it. C plus vector B. Yeah, so we're just distributing the C to each vector by itself. And this makes sense, I think, fairly intuitively. If you think about what each of them are doing, if you think about what addition of vector is and scale multiplication is, and you show things on a graph, you could see these ideas fairly clearly, I think. Okay, so now we have multiply. So far we've done adding and subtracting vectors. Now let's talk, and we've also done multiplying vectors with scalars. Now let's talk about what it means to multiply vectors with vectors. So the first thing that we're going to do is something called the dot product. The dot product of vectors. So there are two principles that we've created as humans of multiplying vectors. The first one is called the dot product, and the second one is called the cross product. One of them is awesome, one of them sucks. Is a simple idea. So let's talk about the dot product, which is the nice one. So the dot product is denoted as this. It's vector A dot, for the dot product, vector B. This will return C. Not vector C. C. It's going to return a scalar. It's going to return a number. The best way to... Actually, I'm not going to do the best way to describe this, because the best way to describe this is too easy. Let's talk about some very simple rules. That C, as a rule, will equal the magnitude of vector A times the magnitude of vector B times sine, is it sine or cosine? It's cosine. Cosine times, let's try purple, times, stop deleting my stuff. It's because I think that I have my finger touching my iPad. Times cosine of theta. Now, what is theta? Theta equals the angle between vector A and vector B. Sorry, I forgot the and. Okay, so it's the magnitude of vector A times the magnitude of vector B times cosine of theta, where theta is the angle between them. Let's show exactly what I mean by theta. Let's go over here and let's erase some of this stuff. No, stop erasing the lines. I want the lines. Sure, why not? That's good enough. No, it's not. No, it's not good enough. I don't like how it selects the entire thing. It's a little bit annoying. Whatever. Good enough. So, okay, so let's show exactly what I mean. So imagine, what were the colors exactly? It's purple and blue and red. Great. Blue and red for the vectors. So let's keep that consistent. So blue. So imagine we have a vector over here. This could be vector A. And then imagine we have another vector over here. Let's say it looks like this. This is vector B. So what does theta mean in the equation, the magnitude of vector A times the magnitude of vector B times cosine of theta? What does theta mean? Well, what we would do is we would simply, what would we do? I believe that we would come up like this, and here, let's move vector A out of the way a little bit so that we can properly get vector B in here. So what we would do is we would take, no. Oh no, I really messed myself up, didn't I? Just select some basic things. We would take this, we would put it like that, and then we could say that this, in purple, right? Yeah, that's theta. That's the theta we're concerned with. And it's cosine theta. So what does cosine theta mean? Well, let's think a little bit about what cosine theta really means in an important sense. Let's think about it for a second. So what is cosine of 0? Well, the cosine of 0 is 1. So if they're right, if the angle of vector B and the angle of vector A are the same, then the scalar property, notice by the way that we are getting a scalar back, because this is a scalar, the magnitude of vector A is a scalar, the magnitude of vector B is a scalar, and cosine of theta is a scalar, so we're getting a scalar back. So if they share the same angle, if the difference of angle between them is 0, then it's just going to be the magnitude of vector A times the magnitude of vector B. If, on the other hand, they're perpendicular, such that theta is 90 degrees, then cosine of 90 degrees is 0. And so the dot product between two vectors that are perpendicular is 0. So those are the two basic rules you should remember with dot products, that if they share the same angle, then it's just going to be the magnitudes of both of them combined, and if they don't, if they're perpendicular, then it will just be 0. The dot product will be 0. Let's also demonstrate something visually. So let's erase my vectors, and I'm going to draw more useful ones. So what were they again? Blue and red? Yeah. So imagine we have a vector like this. A little bit longer. Here, we'll say that this is vector A. And imagine we have another vector, let's say like this. we could say that this is vector B. Okay. What we could say is that we know that the dot product will be, so this is theta over here. We know that the dot product will be the magnitude of vector A times the magnitude of vector B times cosine theta. Well, what is the magnitude of vector B cosine theta? The magnitude of vector B cosine theta, that is the horizontal component of vector B with respect to theta. So let's show that. So this is the magnitude of vector B cosine theta. So that's just an interesting, cool thing. And then, as you can see, of course, if vector B had an angle of 90 degrees, then theta would be 90 degrees, and the horizontal component would be 0, which makes sense. Okay, I think that is basically it for the dot product for now. One thing that's very cool is that using the dot product, we can prove something, which you may have heard before. You may have heard of something called the law of cosine. If you haven't, we're going to prove it right now using the dot product as our thing. Okay, so yeah, this was a complicated thing that I remember from class that I'm not 100% versed in, but really what this shows, yeah. Okay, let's draw a diagram over here. The law of cosine, the dot product will prove the law of cosine, which tells us that no three sides of a triangle are independent, that they all depend on each other. And it doesn't matter what kind of triangle it is. So imagine we have a few vectors. So let's say that this is vector A. You know, I actually drew this diagram way too big. Okay, you know what? For now, it'll be fine. Imagine we have this is vector A, and we have another vector like this. This will be vector B. So we could say, with our definitions that we've established, that vector C is vector A plus vector B. So this will be vector C, right? Vector A plus vector B. This is vector C. So let's show everything. So this is vector B, and this is vector A. Great. All right, now let's write things down a little bit mathematically based on that diagram, which we still have in the other page, which we will go back and reference. We can say that vector C, I think that this was the right color for vector C. No, it was not. We could say that, I think vector C was in red, yeah. We could say that vector C equals vector A plus vector, oh boy, I don't want that kind of plus. You know, I also don't want that kind of equals, to be frank with you. Vector C equals vector A plus vector B. So now let's go through this and add the appropriate signs. So vector C equals vector A plus vector B. Great. And with this, we can also say that, remember, quite simply, we could also say, and this should be fairly intuitive, what I'm about to show right here, that vector C dot, the dot product of vector C and vector C, so vector C dot vector C, stop with the thing, just want a dot, vector C dot vector C equals, I wish I had like more colors easily accessible to me, so I don't have to switch so much, but that equals dot, I made this a little bit too big, didn't I? Plus, that equals vector A plus vector B plus, with the dot product of vector A plus vector B, right? This makes sense. This makes perfect sense. Just by definition. So if vector C equals vector A plus vector B, then the dot product of vector C is the dot product of vector A plus vector B. Okay, now things are going to get a little bit complicated for me, I think, because this is a complicated proof. I'm not going to lie with you. I'm not going to lie to you. So imagine, let's go back and let's establish theta. Let's say that we're given the angle theta over here. That's angle theta. So we could, and we're not going to use that yet, but I know we're going to use it later. So it's confusing. But, and no, I'm going to switch for black now for the rest of the proof because it's just a little bit annoying to switch between all of them. We could say that yeah, we could say that the absolute value, okay, remember all of these are scalars, right? Vector c dot vector c is a scalar. And that vector c dot vector c is the same thing as vector c, the absolute value of vector c squared. Why? Because vector c shares the same angle with vector c, obviously. So it's simply going to be the magnitude of vector c times the magnitude of vector c. So it's simply the magnitude of vector c squared. It is the dot product. So that would equal, and these are all scalars as well, so that would equal, we could, yeah, this equals, the other side would be, is this true that it's vector A dot vector A plus B plus vector B dot vector A plus B? Yeah, I think this is true, because we could, yeah, this is just like vector multiplication, so we could just put, yeah, it's just factoring. So that would be the same thing as vector A plus vector B dot vector A plus vector B. Okay, so I think this makes sense so far. And then this equals, how does that equal vector, how does that equal, I'm sorry, I'm looking at my notes right now. I don't fully understand what I wrote. Oh, it's just distributing the two of them. Yeah. Okay, so now this, it follows equals vector A dot vector A. What is vector A dot vector A? Well, just like vector C dot vector C was the absolute value of C squared, because they share the same angle, therefore it's just going to be the absolute value of vector A squared, right? So that's vector A dot vector A, and then we have vector A dot vector B. So that's we can't really simplify that very well. So that's just going to be vector A dot for God's sake, dot vector B. Okay, and then that plus, I really don't have enough room here. It's crazy. If I zoom in, would I like inherently get more room? No, I don't think so. Yeah, I really wish I could like rotate the page somehow so that I have more horizontal space and vertical space. Is that possible? Rotate this page. Yeah, okay. I mean, I might have to do that at some point, but now I'm sort of already in a bit of a rut. So, okay, so that's, yeah. Okay, and then we have, okay, so then we have the absolute value of vector b squared, or rather, that's not what we have. Yeah, we also, yeah, we have plus vector b dot vector a plus the absolute value of vector b squared, like the magnitude of vector b squared. So that foiled, we just foiled the whole thing. And this comes out to, right, okay, that's the end of the proof really, which is crazy. I think. Hold on, something's weird. Right. Right, okay, so now we have to think about, yeah, we need, okay, now, oh my god. So this whole thing over here, this evaluates to, let's go to the next page. This is and this one I will flip clockwise. Okay, this one, and I want to make sure that this makes sense on the stream. So hold on, let me just make sure that this works. On the screw. So hold on. Let's just make sure. Yeah, no. So I'm gonna be able to resize this a little bit. Hold on. Let's just make sure everything's good. Okay, that looks about right. So, okay, forward. Now that whole thing that we had before, this comes out to simply, yeah, the magnitude of vector a squared, which we could write quite simply as a squared plus b squared, and then we have this thing plus plus. So we have this. We have this a dot b plus b dot a, which really just comes down to 2 a dot b. So what is a dot b? Well, this equals a squared plus b squared plus 2, the magnitude of vector a times the magnitude of vector b times cosine of some angle. What is that angle? Well, that is, and we have to go back all the way to the diagram again, that is the angle that A makes with B. So if we were to draw B like this, again, that looks about right, that's basically B. And then we were to draw A like this, then the angle between them is this, which, yeah, that is that angle. Sorry, so hold on. So that is, oh boy, this is a complicated proof, honestly. That is this angle. It's funny because the guy proved it in the lecture in like 2 seconds. So that is this angle. I didn't know that I could do that. So that is, you know, I don't want to make it orange because that's the color of our other angle. Let's make it like green. That is this angle, which looks a little bit like this angle over here. In fact, they are the same angle. So we could call this like phi. That's not a phi. There, that's fine. Okay. So one thing that we should notice very clearly is that, that theta, we've set theta, kind of almost accidentally, theta equals 180, like the entire arc, 180 minus phi, or thigh, or whatever. I never knew how to pronounce it. Which means that what we want over here is we want, when I say over here, the angle that we want in this cosine is we want phi, but maybe all we're given is this angle in the triangle. So we know that cosine of some angle A equals negative cosine of 180 minus, no, I'm sorry, equals negative cosine of, what's the rule? I forgot what the rule is. Is this true what I wrote over here? Oh yeah, this means that this, okay, so this all means, let's let's make this like a new thing. Can I please move to the other page? Thank you, for God's sake. Do I have to rotate this one too? Rotate this page. Yeah, okay. So this means, again, we have it that theta equals 180 minus phi, which means that theta plus phi equals 180, which means that cosine of theta equals cosine of 180 minus phi. Cosine of theta equals cosine of 180. Yeah, because sure. Yeah, that is definitely true. Equals cosine of, I'm writing so big right now, equals cosine of 180 minus phi, because it's the same thing, you just plug in theta in both ways. And then therefore we know that cosine of 180, how? We know that cosine of 180 minus some value equals negative cosine of that value, and you know this by trigonometry through the unit circle, I believe. Yeah, you can visualize that. Oh boy, that's complicated. At least it's complicated for me. Okay, so did I do this all properly? So now that we have oh my god. Now we have sorry, I just got a call. Now we have that negative cosine of theta equals cosine of phi. That's what we have. And sorry. So yeah, negative cosine of theta equals cosine of phi. And so over here where we wanted phi, which we didn't have, we were given theta in the triangle, we could just put negative cosine of theta, which would give us a squared plus b squared plus 2, plus a squared plus b squared, not plus, but minus 2 absolute value of a, absolute value of b, cosine of theta. And this is the cosine rule, if you want to look at it online and stuff. We just proved it, albeit messy, in a very messy manner. I'm going to do this again from scratch. So let's just do the entire proof over. If you want, you could skip for a while. I don't know, but I feel it's important that I have this a little bit cleaner. So I'm going to do it again. Let's do this again. Let's do it all again. So I don't have anything here. I don't like how sometimes it doesn't shift the page. It's a little bit annoying. Okay. Cool. And cool over here. So I'm going to try to do this again without ever looking at my notebook. Yeah. Okay, so first of all, let's rotate this page. Yeah, clockwise 90 degrees, that's fine. And then I want to make sure that this is good on the streaming software. So yeah, that's fine, I think. I could just draw a line from one end to the other and it will come up properly, right? Yeah. Yeah, okay, good. So it's seeing everything. Awesome. Nope, forward. Okay, cool. All right, so now let's set up our thing again. So we have a graph and we have a triangle situation. So let's draw the triangle. We have A, B, and last but certainly not least, we have C. A, B, and C. Okay. Now let's label them A, and let's label this one B, and let's label this one C. Sorry, that's a B. C, and then we're also going to be given some angle theta. Now the cosine rule needs some angle theta. You need to have two of the sides. In this case, I'm imagining we have A and B, and you're supposed to be able to find the length of side C using A and B and the angle opposite to side C. Okay, so let's set this up. So first we can claim, and I'm going to do this all in black, that C equals A plus B, and that you could see very clearly from the graph. Then we could say that C dot C equals vector A plus vector B dot vector A plus vector B. Sure, why not? Let's just put that over here. Okay, it's a little bit weird because we're doing like factoring in reverse, but vector C dot vector C is simply the magnitude of vector C squared, because that's how dot products work. Since the angle is the same, cosine of the angle will just be 1, and so you just get the magnitude of vector C squared. So that equals, and this is, like I said, this is weird because we're doing like reverse factoring, but that equals vector A dot vector A plus vector B plus vector B. So I'm gonna do it like this, plus vector B dot vector A plus vector B. I believe this is correct. You could factor this essentially now and just say it's vector A plus vector B dot vector A plus vector B, and so this was like a reverse factoring type situation. It's a little bit weird that you can do this so easily. It's hard to visualize exactly what's being done, but yeah, it works. Okay, so now that all equals the magnitude vector A squared plus vector A dot vector B plus vector B dot vector A plus the magnitude of vector B squared. Okay. Now this all, let's like rewrite that. So we come over here, we rotate the page. Great. Okay. Let's rewrite that as it equals A squared plus B squared, because we're looking at the magnitudes, plus 2 of the dot products between vector A and vector B. Stop with that. Vector B. Okay. All right, so that's your system so far, and now what we need is we need some angle to put into the dot product. So if we extend out in our minds vector A for a moment, we have this new angle, which is the angle between vector A and vector B, and that we could call phi. And so this equation will equal A squared plus B squared plus 2AB cosine of, I want to make this very clear, it's going to be cosine of phi. Now the problem is we don't have phi, we just imagined phi. We were given theta, and so we need to find a way to relate phi to theta. So let's do that over here. So just looking at the graph quite clearly, you see that phi plus theta will complete a semicircle, which means that their angles must equal 180. So we have phi plus theta equals 180, which means that cosine of theta equals cosine of phi minus, sorry, that was not phi, that was theta, cosine of phi minus 180, right? So whatever cosine of phi is, sorry, hold on, sorry, no, I don't want to say it like this, because we have theta, okay. cosine of phi, whatever cosine of phi is, we don't know what it is, but we know that it equals the cosine of theta minus 180, right? Because that just makes sense that phi equals 180 minus, or rather, no, I'm sorry, sorry, not theta minus 180, but rather 180 minus theta, okay? Now we know that the cosine of 180 minus theta is the same as negative, so this equals negative cosine of theta. And like I said, we know that by the unit circle. Let's actually draw the unit circle over here so we can have an x-axis and we can have a y-axis. And here's our unit circle. That's like a circle. That's a terrible circle. If I hold it, will you just, yeah, okay, there's our circle. And, okay, and we can have here some angle theta, and then that means that this is cosine of theta. And then we can have over here, this would be the same thing, except it's 180 minus theta, which means that this is going to be negative. As you could clearly see that this is going to be the opposite of this one, so that's going to be negative cosine of theta. Okay, great. So with that idea, we could say that cosine of phi equals cosine of theta, and that allows us to plug that in over here. So instead we have this equal to a squared plus b squared minus 2ab cosine of, and then theta. Okay, so now the entire proof, the entire formula written as derived, again, all these equal signs are equaling something. We have c squared equals, c squared equals, a was in blue, I believe, so equals a squared plus, and b was in, what was b in? Purple? I think it was purple. No, a was in purple. Okay, fine, so a was in purple. My bad. C squared equals a squared plus b squared minus, this will be like that, minus 2, and then a, b, 2ab, and then cosine of what? Of theta. Sorry. And that is the cosine rule of triangles proved using the dot product, essentially, is what we've been using. Okay, great. We're not done with the lecture yet. That was just the cosine rule. We have more to do. Okay, there you go. So that's just a little bit of an intro to the dot product. Let's move on. Rotate this page clockwise 90 degrees. Great. And let's erase all of this. Now let's talk about the other way to multiply vectors, and that is the vector product, or the cross product. The cross product will look like this. Vector C, here, nope, vector C equals, and this will be a cross symbol, vector A cross vector B. Oh, by the way, the key thing to note in that proof is that over here, vector A dot vector B equals vector B dot vector A. And it's because the angle between them will always be the same no matter which one you're looking at with respect to the angle. The angle is the same between them. So it's just going to be the magnitude of vector A, which is positive, times the magnitude of vector B times cosine of theta. So you could switch them around. But the cross product does not work like that. The cross product has a very simple rule, which is, imagine you have your vectors. So this will be vector A, and then this will be vector B, B, A, and here we have theta. So the cross product evaluates to vector C. The magnitude of vector C equals the magnitude of vector A times the magnitude of vector B times sine of theta, not cosine, but sine of theta. And theta being the angle between them. So again, that's the magnitude. The cross product yields a vector, but the vector will have a magnitude like this. What will its orientation be? Well, the orientation would be the right-hand rule. Like, that's how we find out the orientation. And basically what you do is you put your right hand along vector A, such that... How would you do this, actually? That's weird. I don't even... Hold on. And then you have to curl your fingers. This is so weird. Because in this case, I know that you have to put your right hand along, but I can't put my right hand along it. I cannot put my right hand along it and then also turn my fingers toward vector B. Like, that doesn't make sense. Unless I put my right hand on the opposite, but then it's the opposite. I don't want the opposite. I want the correct way of doing it. So, yeah, okay. The right hand rule basically says you want to put your right hand along the first vector, such that your fingers are pointing in the direction of the first vector. And then you have to turn your fingers inward. Your hand has to be oriented such that when you turn your fingers inward, they turn in the direction of the second vector. And then the direction that your thumb is facing will be the direction of vector C. Watch a video on the right-hand rule. I recommend it. But in this case, vector C will be pointing into the page, and that's denoted by this. That's the direction of vector C, as opposed to out of the page, which would be denoted by this. It looks like an arrow. For God's sake, like that would be denoted like this. Sorry. If it was pointing out of the page, it would be denoted, shown like this, and into the page is shown like this. So you can imagine, like, if the arrow is going away from you, it looks like you could see like the feathers and stuff, and if the arrow is coming towards you, it looks like a little point. But yeah, in this case, if you put your hand in the direction of vector A and then you turn your fingers toward vector B, you'll see that your thumb is pointing into the page. So you really need 3 dimensions to do the cross product properly. Yeah, I think that is a good explanation. And one thing that my teacher said, which was very interesting. Okay, let's put it. Let's show something. Let's see if I could show this in 3 dimensions, graphically. So, imagine. Let's erase all this. Cool. Imagine we have our, and this is gonna be interesting. Imagine we have our x, then we have our y, and then we have our z axis. So we're making like a 3D situation. So here's, sorry, this is x, this is y, and this is z. So imagine we have one vector, like this, and then we have another vector, like this. So first of all, yeah, so then the resultant vector would actually be the one perpendicular. So the resultant vector from the cross product is going to look like this along the z. Hold on. Yeah, it'll look something like this. Stop it. Stop it! Cool. Like that. That would be the resultant vector in the cross product. So it's always perpendicular to the plane that's made. So a few rules about the cross product. If if the vectors are lying on top of each other like this, then the magnitude will be, I guess the magnitude of vector c first of all will be 0 because the angle is 0 and sine of 0 is 0. And in terms of the direction, well, the direction doesn't really matter if the length is 0, right? So the direction will sort of just be, the angle, the orientation would sort of just be undefined, really. Right. One thing that's interesting is that using the right-hand rule, if you think about it, and I want you to think about it, because it'll be difficult for me to explain. I'm going to try my best to explain it because you have to explain it. You have this idea that vector b cross vector a actually equals negative vector a cross vector b. Because depending on what the first vector that you put your right hand to, and then depending on the turning, that will determine if you're going out of the page or if you're going into the page. Because both of them are perpendicular to each other, but one of them is going in the opposite direction, and that's why it's a negative. I hope that makes sense. I don't know. Okay. So now let's talk about. Okay, now let's talk about how we do some of these operations algebraically, if you will. So let's do this. Let's talk about the components of a vector. So the components of vector A, imagine we have like this, vector A. The components of vector A are AX and AY, and then AZ, and then so on and so forth, if you have 3 dimensions. So AX is the x of vector A. So that would be the magnitude of vector A cosine the orientation of vector A, which we will denote as theta. And then A sub y equals the magnitude of vector A times the sine of theta, which I hope makes sense. So those are the components of vectors. That's how you would understand that. And then we can say that. So now let's talk about how some of the things, how some of the operations that we've been talking about work. So I'm not sure what I have written over here. A sub x squared plus ay squared equals a squared cosine squared theta plus. Right. This is just the Pythagorean theorem at this point. But let's show it using the definition. So if this be true, then we have the idea that we would assume that the magnitude of vector A, which would be the hypotenuse, equals ax squared plus so the magnitude of vector A squared equals ax squared plus ay squared, right? That would be the idea. Because this would be vector A, and then this would be ax, and then ay, ax, ay, and so ax squared plus ay squared should equal the magnitude of vector A, right? Based on the Pythagorean theorem. So let's break it down. So we would say that, let's come over here, we would say that the magnitude of vector A squared equals, so what is ax squared? So ax squared is just the magnitude of vector A times cosine of theta squared, right? That's ax squared. Plus ay squared would be the opposite. It's the magnitude of vector A sine of theta squared. Okay, well, what is the so since this is multiplication, we could simply put the square on both of them. So this would be equal to that's equal to the magnitude of vector A. Sorry, this all needs to be vectors. The magnitude of vector A squared cosine squared theta plus the magnitude of vector A squared sine squared theta. Okay, so there you go. So because of that, we could do some factoring. So we could simply say that this is just the magnitude of vector A squared times cosine squared theta plus sine squared theta. And just using the unit circle as a definition, we know that this evaluates to 1, which means that all we're left with is the magnitude of vector A squared equals the magnitude of vector A squared times 1, which makes sense. So there you go. That's how components of vectors work as like a definition. That is like the definition of components of vectors. So now let us move on. And let's talk about, okay, so this will be the last thing for the lecture. Let's take a look at the dot product again. So, sorry, remember the dot product? The dot product said that vector A dot vector B equals the magnitude of vector A times the magnitude of vector B cosine theta, right? Let's talk a little bit more about what this means algebraically in terms of their components, and this all the way by equals C. So what is C? C is a scalar. So we could say that C equals, and this is really the definition of a dot product. This is what dot product means. It means vector AX times BX plus AY times BY dot dot dot, like, and then AZ times BZ, A whatever times B whatever, forward and forward until, and then you do it, and then you sum it all up. You sum all these products, and then you get C. So why is it that this evaluates the magnitude of vector A times the magnitude of vector B cosine theta? Well, we didn't go over that in class, but I figured it might be a fun thing to try and prove. So let's keep this all here, and let's erase this proof over here. Let's see if we could figure this out. So yeah, we have that. Why can't I erase this? That's weird. There's like a drawing there that I can't erase. That's interesting. We have. Okay, I actually don't know how to prove this. Let's just think about it. Cosine theta. That's interesting. The magnitude of. So what is the magnitude of vector A in terms of its components, right? Let's put that over here. So, by the way, that's the end of the video for now in terms of going over the lecture. This is just me trying to prove the dot product. So let's see. So the magnitude of vector A equals the square root of A sub x squared plus B sub x. Plus A sub y squared. Yeah, that's all I got. Trying to see how these two connect. I don't know. Okay, I'm going to end the stream now because I've gone over all the notes from the first lecture. And I'm probably going to watch a video proving how the dot product comes out to the magnitude of vector A times the magnitude of vector B times cosine theta. But anyway, that's the video for today. I'll see you guys in the next one probably. This was intense. Yeah, thanks for watching. I'm going to end the stream. Bye.